Hello everyone, my name is Aishwarya. I am currently a performance and capacity engineer at Facebook. I am going to present our work, Mediating Power Struggles on a Shared Server. This work was done in collaboration with my advisor, Dr. Anand Sivasubramaniam, during my PhD at Penn State. This is an illustration of typical power infrastructure in a data center. A data center sources its power from the grid or from on-site supply. It is then distributed to the end servers using a hierarchy of power devices. A data center also requires backup power infrastructure such as energy storage devices and diesel generators to deal with power supply outages. Data centers are constrained in their power capacity. For example, data centers typically right size or oversubscribe their power infrastructure for cost benefit. This imposes a static power capacity limit. In addition, data centers can participate in demand response with the power grid for cost benefits or integrate renewable power supply sources for carbon benefits. Therefore, in addition to the static limit imposed by the physical infrastructure, there could be dynamic power capacity limit in a data center. Servers are the end units that consume power in a data center. Therefore, any data center level power constraint gets translated to server level power constraints. If we look at today's servers, they are brawny machines with plentiful cores, cacheways, and memory capacity. Therefore, data centers host multiple applications on the same server and carefully isolate the applications from each other in their direct compute resources such as cores, caches, and memory. However, when data centers and consequently servers are constrained in their available power capacity, these applications can still contend for the indirect resource of power which is used in all the direct resources that is needed by an application. We refer to this as a power struggle. In this work, we focus on how to mediate power struggles on a shared server. We pose it formally with an objective of maximizing the aggregate throughput of a server. This is the sum of all its applications throughput normalized through its throughput without any power cap. Here, the constraint is that the total power draw of a server should stay within the capping limit. The power draw of a server comprises of its idle power, chip maintenance power, and the dynamic power for all its applications. Idle power is the power consumed by a server regardless of whether an application is running or not. The server expends certain amount of idle power because of leakage current, DRAM refresh, fans, and storage components. In addition to idle power, turning on a core to run an application also turns on certain uncore components like LLC, on-chip network, and memory controller, which we refer to as chip maintenance power. Rest of the power goes towards the aggregate dynamic power needs of all the applications that's hosted in the server. Note that we have multiple power allocation knobs in a server. For example, we have core consolidation, in which we can consolidate our applications to a few codes and keep the rest of the codes in a deep sleep state, which will allow us to save power. We also have per core frequency scaling to scale up or down the frequency of individual cores. In addition, we also have DRAM RAPL interface to allocate power directly to DRAM. Note that each of the knobs offers several settings for tuning. In addition, energy storage device is an additional knob for control. It has to be charged or discharged depending on its usefulness to the application. And it also requires coordination of its charge power and discharge power to stay within the available power budget of a server. This is a huge space to search in order to meet our objective. So we focus on exploiting the unique properties of power as a shared resource in order to develop heuristics for power allocation to mediate power struggles. What are the unique properties of power? Unlike direct resources like CPU and memory, power is an indirect resource consumed by the direct resources in a server. This mandates a coordinated control of power across different direct resources. Second, power cannot be multiplexed in space. Consider two applications requiring very different set of resources. example, high CPU for one application and high memory for other application. They can coexist on the same server without much direct resource interference, which we call multiplexing in space. On the other hand, these two applications can consume completely different set of resources, but each of these resources in turn consumes power. This leads to power struggle depending on how stringent the power capping threshold of the server is. So we need to manage power explicitly and not as a consequence of managing other resources in order to better manage power struggles. Direct resources are compartmentalized. For example, CPU capacity may not be shifted to increase memory capacity even if it is underutilized. In contrast, power is fluidic, allowing its consumption in one component to be seamlessly shifted to another based on the application needs. This is one benefit of being an indirect resource. The next property is non-convexity. The relationship between usage of other resources and power can be non-convex. That is, the incremental use of server cores does not translate linearly to the corresponding incremental power draw. As we will show later, this trend leads to poor use of power and leads to energy disproportionality under stringent power limits. The next property is time shifting. Power can be shifted in time using energy storage devices by temporarily boosting power when supply is constrained. And the energy storage devices can bank energy when there is adequate power availability. With such devices, power availability and demand can be shifted in time, which is not possible with most other direct resources. So the question that we want to answer is, can we make use of these properties to develop heuristics for power allocation in shared servers? Recall that power cannot be multiplexed in space. Therefore, when a server is imposed with a power limit, we not only cap overall server power draw, but also cap power for each application. So we first need to answer the question of how much power to allocate for each application. This figure shows the performance of two applications, App A and App B, with their respective allocated power in x-axis. Say we have to reduce server power draw by 20 watts, how do we apportion this gap between the two applications on the server? We can remove 10 watts of power from each application, which will result in significant loss in performance for App B, while App A is little affected. Instead, removing 5 watts from App B and 15 watts from App A would result in higher overall server throughput. This example illustrates that when we cap power for each application, we need to be aware of application level differences in the utility of power. As power is an indirect resource, identifying how much power to allocate for each application alone will not suffice. We also need to identify how to further apportion this power across different direct resources in an application. This figure shows the relative utility per watt for each of the direct resources in our experimental platform for the two applications. App A is more memory intensive than App B. Therefore, it benefits substantially more in having additional watts devoted to memory. In fact, this is even more beneficial than adding an extra core or boosting frequency. This is in contrast to the resource level power utilities of the compute intensive application App B. This illustrates that by being aware of resource level power utilities, we can make effective use of the space shifting property. Even after identifying how much power to allocate and where to allocate, we need to coordinate the use of power across application to stay within the power limit. For example, let us consider that a server has a power capping limit of P cap as shown in this figure. A part of this limit goes towards idle power. This is the power consumed by the server at its deepest socket sleep state. Another part goes towards chip maintenance power to maintain the uncore components, and it's required as long as any core needs to be active. And only the remaining power is used to host applications. Utilizing the available headroom, the server can time multiplex the applications one after another, or coordinate them in space and let them run simultaneously. Note that the latter is more beneficial than the former, as the private cache states will be preserved for the applications. More interestingly, can energy storage help improve power efficiency under power struggle? Let us consider the case when power cap is just as much as the power needed towards the idle power and ship maintenance power of a server. Under the stringent power budget, the server will not be do any useful work at all. This is where the time shifting property of power can help. The server can be put to deep sleep state and use the power which was originally intended for chip maintenance towards charging the battery. Once the battery is charged, it can use the battery discharge to boost available supply to exceed power cap and perform useful work. More importantly, we can coordinate power use between applications to exceed the non-convexity problem when using energy storage. For example, let us consider that app A and app B needs two cores each to run. We can charge the battery for 10 seconds. Assuming that it's an ideal battery, this will provide us discharge time of 10 seconds. If we run app A and app B one by one, each of the application will get 5 seconds each. Instead, if we could coordinate these applications to use their respective cores at the same time, we will expend less energy on chip maintenance power. Therefore, more of the available power will be used towards performing useful work for the applications. For example, assuming a chip maintenance power of 20 watts as in our experimental platform, this increases power availability from 5 seconds in the former case to 6.5 seconds in the later case. We developed a prototype in Linux which puts together all these heuristics on power allocation in a shared server. The paper has more details on challenges in implementing these heuristics and a solution to address them. For example, we may not have the power utility curves a priori and we need to build them online. Similarly, the system needs to adapt to dynamic scenarios such as changes in power cap limits, application arrival, departure, and phase changes. We evaluated our prototype on Intel Xeon 2620 server, which provided us with the following knobs for allocating resources and managing power. It has 12 cores which enable us to perform core consolidation and keeping the rest of the cores in idle deep sleep state. And it also allows for per core frequency scaling and DRAM RAPL to allocate power to DRAM. We can also put the socket to its deepest state by keeping all the cores in idle state, which will allow us to charge and discharge battery, which is a lead acid battery connected to our server platform. In this talk, we show the key results and insights from our prototype on 15 random pairwise combinations of throughput-bound application. These applications are representative of data analytics, graph analytics, media processing, and search indexing workloads. The paper has more details on the experiments with latency critical workloads and performance under different dynamic changes in the system. We first present server level performance benefits of our approach under a linear power capping threshold of 100 watts. Note that the server reaches peak power draw up to 130 watt and the 100 watt represents approximately 77% of its peak draw. We study the aggregate throughput of the servers across all the 15 combinations, and the throughput is normalized to the throughput of the server in the absence of any power cap. Our goal is to compare the performance of the two heuristics applicable for lenient power cap, that is, application utility awareness and resource utility awareness. We compare it to the following baseline power allocation policies. Our first policy for baseline is utility unaware power capping, which allocates power equally between the applications using hardware allocation knob of wrapper. Our next policy is server plus resource aware allocation, which is aware of resource level differences in power utility in a server, but it is application unaware. It uses core consolidation, frequency scaling, and DRAM power allocation, where the utilities are calibrated across all the applications. These two policies serve as our baseline, and they reach an average throughput of 60% with respect to the server throughput without any power caps. We next compare the results of app power policy, which incorporates our first heuristic to allocate power to application based on utility of each watt. This provides 7% improvement in throughput compared to the baselines. When we add resource awareness on top of it, it improves the gain by another 7%. The performance benefits come from application level differences in power utilities. We illustrate that using two applications, X264, a video codec benchmark, and single shows shortest path, a graph benchmark. The x-axis shows the dynamic power allocated to the applications, and the y-axis shows their normalized performance with respect to no capping. As we can see, these two applications differ significantly in their power utilities. For example, if we have only 30 watts to allocate to these two applications, allocating 50 watts each will be a poor choice. X264's performance drops significantly. In contrast, allocating 20 watts to X264 and 10 watts to shortest path is beneficial for overall server throughput, which is what the app-aware policy does. In addition to application level differences, these two applications also differ in their resource level power utilities. X264 derives higher performance per watt from CPU cores, whereas single source shortest path derives higher performance watt from core frequency. App plus resource aware power allocation policy achieves better performance by considering these differences into account. We next study the performance at a stringent capping threshold of 80 watts, which barely provides 10 watts over idle and chip maintenance power in our servers. This is around 60% of server's peak power drop of 130 watts. Even in this setup, we use utility unaware and server plus resource aware policies as our baseline. These baselines provide less than 20% of the throughput of the uncapped server at a power capping limit of 80 watts. Adding app and resource awareness further increases this throughput to 30% with respect to the throughput of uncapped server. Adding time shifting using energy storage helps us increase the server throughput to 42% as it addresses non-convexity by reducing energy spent on chip maintenance and allocating it to do more useful work for applications. This shows that energy storage can help improve compute efficiency and provide better energy proportionality at stringent power caps. We next show the cluster scale benefits of our approach. We consider the scenario when the cluster performs peak shaving. The figure on the left shows the dynamic power caps of cluster to shave 30% of its peak power draw from a publicly available cluster power trace. We replay these power caps on our prototype of 10 servers and compare 3 policies for power allocation at cluster scale. The first policy is to allocate available power equally to all servers using RAPL. The second policy is also to allocate power equally but uses the proposed heuristics. The third policy is slightly different as it powers only as many servers as allowed by the cluster level power budget, hence a power cap is not imposed on any active server. As we can see, the proposed heuristics provide over 12% improvement in cluster throughput compared to equal allocation of power using RAPL. It is comparable to or better than the server consolidation approach by 3 to 5%. To conclude, applications can contend for the indirect resource of power in a shared server. We exploit the properties of power to mediate power struggles and improve overall energy efficiency by identifying 3 heuristics. First, we exploit heterogeneity in application level power utilities. Second, we exploit heterogeneity in resource level power utilities across applications. Third, we make use of energy storage to address non-convexity. Our experimental result shows 20% improvement in throughput at server scale depending on the stringency of power cap and 3 to 12% improvement in throughput at cluster scale when doing peak shaving. Thank you very much for listening to me talk.